Welcome to this puzzle Kickstarter session. We will be continuing with our discussion on the well-ordering principle. In this lecture, what we will be doing is proving the what is called principle of mathematical induction. And I don't want to recall anything. Let us just get right on with it. So first, let us discuss what is called the V conduction. So consider a function f, which takes natural numbers to this two-element set. Instead of 0 or 1, you can think of it as false and true. And f could mean, the truth or false value of the nth statement. So fix some natural number n, and the value that f takes could just indicate whether the nth mathematical statement is true or false. So what do I mean by that? So the nth mathematical statement is, let's say, for example, that the first n natural numbers sum up to this number. So this could be our nth mathematical statement. The first mathematical statement would then just mean that the sum of the first one natural number, which is just this natural number, sums up to 1 into 1 plus 1 by 2, which is of course 1, and that is true. The sum of the first one natural numbers is of course 1. The second statement would be that this summation is 2 into 2 plus 1 by 2, which is also true because this is 3 and that is also 3. So f just records for which values of n this particular mathematical statement is true, for example. So that kind of thing. It could also be some more complicated thing, but for an example, that is good enough. Okay, so suppose we have these two hypotheses on f, that f1 is equal to 1, meaning f of 1, meaning the first mathematical statement is true. And the second condition that we insist that f satisfies is that if f of n equals 1, meaning if the nth mathematical statement is true, then the n plus 1th mathematical statement is also true. So with these two conditions, we want to show that actually f of n equals 1 for all n greater than or equal to 1. Meaning all the mathematical statements are true. And this is how induction works. I'm sure you're familiar with it from high school. Okay, so this is intuitively obvious. There's nothing very interesting going on here. So for example, f of 1 is 1. This is given to us. And now if you substitute n equals 1 in this statement, what do we get? We get, since f of 1 equals 1, f of 1 plus 1 is also equal to 1, meaning f of 2 is 1. Then you substitute 2 in this statement and you get f of 3 is 1, and so on. So this will never stop this process. But this language that, well, this process will go on, and this kind of language is not mathematically precise, at least not to me. And well-ordering principle can be used to, actually do it formally. So here is a proof why the well-ordering principle. So let B be those natural numbers for which f of n is 0. So again, this secretly stands for set of all the bad natural numbers. If B is empty, then we are done. If B is non-empty, then let n naught equals the minimum element in B, and by the well-ordering principle, this lies in B. So n naught is an element of B. This is the smallest bad natural number. Clearly, n naught is greater than 1. Why? Because n naught lies in B, and 1 is not in B, because f of 1 is 1. 1 is not a bad natural number. F of 1 is 1. So n naught is greater than 1. Therefore, f of n naught minus 1 equals 1, because n naught minus 1 is a natural number, since n naught is greater than 1, and it is not bad, because n naught is the smallest bad natural number. But then by 2, f of n naught minus 1 plus 1 should also be equal to 1, immediate from this condition, which implies f of n naught equals 1, which implies n naught is not in B, which is a contradiction because n naught was an element of B. That's what the well-ordering principle told us. And that's it. That's why this statement is true. So this may seem like a long-winded reasoning, but I like it. Okay. So there is also something called the strong induction. I will not prove it. This will be an exercise, but let me read out the statement. So it says that again, f is some function which records, this is supposed to be recording the truth and false values of a sequence of mathematical statements. With f of 1 equals 1, this is called kind of the base case of induction. That's what this condition is supposed to be. And the second condition is a little bit different from the previous one. It says that f of n plus 1 is 1 if the value of f on all smaller integers, smaller than this, is 1. So in the previous one, we just had f of n equals 1, where n is the immediate predecessor of n plus 1. Here we are saying f of all predecessors of this guy is if all predecessors of this guy have the property that f takes the value 1 on them, then f takes the value 1 on this guy also. So it's a little bit different from that. This is usually referred to as strong induction. I mean, this conclusion that with these two hypotheses, you can show that f of n is 1 for all natural numbers. And again, this has the same proof as the previous one, and I leave that as an exercise. So now let us use this to prove something very, very basic. Again, it is something which I hinted at earlier, which I'm sure we know this from high school. So for any natural number n, we have this equation. The sum of first n natural numbers is that expression. And this is something that we can prove using the principle of mathematical induction. In fact, V induction will suffice. So define f from n to 0, 1, or maybe I'll say false and true if so we define this as f of n equals true if the sum of the first n natural numbers is indeed that, and false otherwise. Okay, so that's how we define f. And note that we have f of 1 is true. That's clear. That's just by substituting n equals 1, of course, this is true. And suppose if f of n is true, then we have 1 plus 2 plus 3 plus this equals n into n plus 1 by 2, which implies, well, the above thing plus n plus 1 equals this plus n plus 1, which if we just compute, we will get the right hand side is that, which implies f of n plus 1 is also true. And that's it. Therefore, f of n is true for all n, for all natural numbers n, and this is what we wanted to prove. Saying that f of n is true for all natural numbers n is exactly the statement of the theorem. And that's it. So this is an example of mathematical induction. And let me maybe give an exercise. Try to show that 1 square plus 2 square plus 3 square plus this is equal to, if I remember correctly, this turns out to be this, for all natural numbers. Again, it's the exact same idea as this proof. So this was a very simple lecture. I'm sure we've already seen all these things in high school. Maybe not quite this way, not quite by way of the Velodrome principle. I think we take this as a statement for granted. For one, it is easy to take this for granted. It is already very intuitively obvious, and this can be used to prove the Velodrome principle. Either you take the Velodrome principle as basic, then you can prove this, or you take this as basic and you can show the Velodrome principle and so on. I like the Velodrome principle as a more basic fact. Alright, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.